Okay, so today, thanks for coming, everyone. And we have a double header. Two researchers from Sandia National Labs. We're going to start with an old colleague of mine, a mentor, perhaps, if you will, from Waterloo days. So it's a pleasure to introduce Robin Blume-Kohout, who will talk about errors and are we still using QCVV as an acronym these days, or is that dead?
I think that would be entirely appropriate for this talk.
Sure, QCVV. All right, take it away, please, Robin.
Thank you, Chris. Well, hi, everybody. It is great to be back staring into the green dot at the top of my monitor. I was really excited when Chris invited me to give a talk, and I've enjoyed the heck out of all of my trips to Australia. And then he explained that I wasn't actually going to be making a trip to Australia, and I sort of pouted for a couple of days. But the nice thing is, because of the fact that we're on opposite sides of the world, it's bright and early on a Friday morning over where you are. But for me, it's actually 8 o'clock in the evening. And so in honor of all my wonderful times in Australia that I don't entirely remember, I'm actually going to open up a beer just for old time's sake, because I feel like that's pretty much all I ever do when I come down for Coogee or whatever else. So cheers. And I'm awfully sorry that it's 10 o'clock in the morning, although Mick right now is saying it's 10 o'clock in the morning, so what? So Erik and I are, the plan is to do a double header here because, as you guys might know, the APS March meeting got canceled the day before it actually started. I was one of the lucky few people who happened to actually be in Denver when it was canceled and then walked around the deserted conference center. So we have these talks that are sort of stashed and never got to get given. So this is the talk that I was going to give at the March meeting. And if you've been to the March meeting, you know that you have 12 minutes to give your talk, and you would darn well better give it in only 10 minutes. So I've got 30 minutes to give a 10-minute talk, which is absolutely fantastic and lets me do silly things like crack open a beer and also kind of dawdle a bit, take my time, and take questions. So this will be really almost an advertisement talk unless you ask me questions, and you can do that at the end, but you're totally encouraged to do that in the middle, interrupt, raise your hand, and one of the moderators will see you and interrupt for you. And ask me to go into more detail about whatever. The paper, I hope you can see it on your screen there. In fact, why not go download it right now? Then you could possibly follow along. This paper was posted to the archive almost a year ago. And since then, as we've been working through the review process, referee B, if you're out there, stop it. We've actually been like legitimately figuring out more things. So if you ask the right questions, I might even go a little bit beyond what's in the paper and explain some of the things we figured out since then. But without further ado, what I want to talk about is crosstalk. I actually want to just pause. I would take 15 seconds of silence during which I want you to think about what crosstalk in quantum computing is. Do you know?
Yeah, are we supposed to guess? I can take a guess.
No, I just want you to think silently and figure out whether you think you know, or are you not sure, etc. But Chris went and screwed it up by butting in the middle. So now that we've all missed out on our moment of silence.
Well, Nathan's here too, so thinking silently is out of the question.
Yeah, and nevertheless, who broke the rule,
So my group at Sandia is the Quantum Performance Laboratory. One of the things that we do is we serve as the test and evaluation team for IARPA's logic program. IARPA is one of the US government funding agencies, and they are sponsoring a program with 4 different performer teams to build a logical qubit. Hasn't been done yet. There have been some claims, but I would say it really hasn't been done yet. The For instance, the cat qubits out of the Sholkov group are not actually what I would call a logical qubit. They use a kind of error correction to make a better physical qubit. Nobody has really built a fully protected quantum error correcting logical qubit yet. And so there's these 4 performer teams, all of which are supposed to build one successfully within the next 18 months or so. We've been at this for 3 years now. Our job was to come in and understand what they were doing and whether they were doing it well enough. And one of the things that we had to do was to quantify the crosstalk. Okay, so we started thinking about doing that. And eventually we realized that we didn't know what crosstalk was. And then we ended up realizing that it was a bit of a red herring, because crosstalk is a physics phenomenon or an electrical engineering phenomenon. It actually, if you look it up in the dictionary or Wikipedia or something, it refers to when you've got some wires and the signal from one wire goes over into the other one or vice versa. You can also have this with laser lines, any sort of communication line. It's not really a concept that applies directly to quantum computers or multi-qubit quantum processors. So we kind of stepped back and said, what exactly are we trying to do here? And that's the story that I'm going to tell you over the next 20 minutes. And it's a story that starts with the transition on this slide from qubits, which, I mean, even when I came into the field a yonk ago, we had qubits. We had NMR, we had photons, we had all kinds of 2-state systems that were in the laboratory and getting better. We had 1 qubit, and sometimes we had 2 qubits. But in the last 5 or 6 years, we've started to see lots of qubits. Quantum processors like the IBM Q pictured here. And someday we're going to have fully functional quantum computers like this fantasy picture described down at the bottom here. I've always assumed that I'm this guy here with the lab coat on and the bar chart, trying to figure out whether these people are actually doing it correctly. So this transition from qubits to multi-qubit systems to all-up quantum processors that pretend to be quantum computers is just, it's an evolutionary process. We started with 1 qubit in the laboratory, and some technologies, electrons on helium, are still pretty much there. Then they moved to the stage of 2 coupled qubits and trying to couple them properly. And semiconductor qubits are still pretty much here. And after that, you move into what I would call 3 to 100 connected qubits. The next stage after that is probably 1 logical qubit, because error correction is going to be important. And then honestly, we don't really know what all the stages beyond that are, but eventually we get down here to actually useful quantum computing. The state of the art today is somewhere between 2 coupled qubits and 1 logical qubit. So each of these stages has a different control paradigm that brings different challenges. At 1 good qubit, the control paradigm is you have full control of the entire state space. You can use your microwave generator or your laser or whatever to pretty much dial in whatever unitary you want. There's some noise there, there's some decoherence, but you can do whatever you want. SU2 is just a broad featureless plane. Once you get to 2 coupled qubits, the challenge here is typically executing a 2 qubit entangling gate. So you have 1 qubit gates on each qubit individually that are typically very good by the time you've reached this stage of maturity. But the 2 qubit gate is the challenge. Today, error rates below 10 to the minus 4 on single qubit gates are pretty normal. Error rates below 1%, 10 to the minus 2 on 2 qubit gates are remarkable. When you move to more than 2 qubits, 3 to 100 connected qubits like this, now the assumption is you have local control, you have pairwise control, the ability to do entangling gates, and this is where crosstalk becomes really important, whatever it is, and also parallelism becomes important. We have a transition from doing gates in sequence and thinking of control as gate, 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 one after another, to gates happening in parallel. And there's a question of, if you have an instruction that tells you to do a bunch of Hadamard gates in parallel or a bunch of CNOT gates in parallel, do you actually do them in parallel? Do you break them up into series? How exactly do you arrange these things? We move from gate sequences to quantum circuits. And then at the logical qubit stage, new challenges appear. But I really want to focus in this talk on this stage 3 of connected qubits. So back in 2017, when we started doing this, we had the idea that crosstalk is one of the bad things that happen when you have 3 or more qubits. Since then, we've kind of changed our perspective. And by last year, we'd come to the conclusion that crosstalk means pretty much all of the bad things that uniquely happen to 3 or more qubits. And I'll explain what I mean by that, but I actually do mean this, that essentially everything that goes wrong with many qubits constitutes some kind of crosstalk error. To introduce that, let me ask you to think again. How would a quantum processor behave if it had no crosstalk at all? And if you think you know what crosstalk is, then you may have an answer to this. If you don't necessarily know what crosstalk is, as we realized that we didn't, then this is a question that helps you figure out what crosstalk is. Intuitively, none of the qubits should talk to each other. That would be crosstalk between 2 qubits. Unless, of course, we're actually doing a 2-qubit gate on these qubits, in which case we definitely want them to talk to each other. So it's not crosstalk if we told it to do it. The conclusion from this is a simple point. Crosstalk is intertwined with control over the qubits. What counts as crosstalk is unwanted coupling of any kind. If it's desired coupling, then, well, either you wanted it or it's not exactly what you wanted, but you still did want some coupling. And so if a pair of qubits that you're trying to do a CNOT on doesn't do what you want, it's not really crosstalk, it's just a bad gate. But if 2 qubits are supposed to be just sitting there and they get entangled, that is crosstalk. But it's not the only kind of crosstalk. So to figure out, to give it a rigorous definition of crosstalk, we have to look at the control that we're doing. We have to look at the program that we're running on the quantum computer. So here is a sample quantum program. This is a quantum circuit, right? We've all seen these. These are shown in Nielsen and Chuang, and we see them every day of our careers once we've opened Nielsen and Chuang, more or less. So in this circuit, I have 4 qubits. They get initialized, and then they have short, happy lives with gates getting executed on them, some 1-qubit gates, some 2-qubit gates, and then at the end, they get measured. Sort of like the life story of a cow or a sheep or something, right? You're born, things happen to you, and then you get sacrificed and turned into classical information. So at a very minimum, if you have a quantum processor or a quantum computer, it should be able to run circuits like this. And it should be able to run them repeatably. This sounds like a trivial statement, but actually, quantum processors drift a lot. And when we started investigating crosstalk, we realized that drift was a huge problem for a whole bunch of reasons that I don't plan to get into unless somebody asks me about it. It really screws up an attempt to detect or characterize crosstalk. So we start by assuming that we can run this kind of circuit reliably and repeatably. If I run this circuit every microsecond for the next 12 hours, I should be sampling from a stable distribution of outputs. If I'm not, if I see that things are drifting all over the place, I don't even want to try to define crosstalk at that point. So let's assume that it does, our processor does run circuits like this one reliably, that I can talk about the output distribution. Then in order to start defining crosstalk, I need something else. I need my processor to also be Markovian. Again, if it's not, I don't even want to start trying to define crosstalk. What I mean by Markovian is that this circuit can be divided into layers. Here's an initialization layer. Here's a layer of gates. Here's another layer of gates. Here's another layer of gates. Boom, boom, boom. In other words, this is a sequence of operations. Quantum circuits are sequences of operations. And if those operations are not independent of one another, if, for instance, the second blue layer here acts in a different way depending on what came before it, if there's something around that's serving as a memory, then all hell breaks loose, and I don't want to try to define crosstalk. So I'm going to assume that the behavior of the processor is Markovian and that I can talk about circuits as a sequence of independent layers that can have noise in them, but the noise is not dependent on what came before.
Okay, Robin, can I just push back a tiny bit?
Sure.
Or at least, are you saying that outside of these contexts, crosstalk doesn't exist? Or are you just saying that it's too hard to get to grips with because it's entangled with everything else that's going on?
I'm saying that it's too hard to get to grips with. Now, really what I mean is, for God's sake, let's define it in this context first. Once you've defined it in this context, and once you have some ideas about how to model non-Markovian behavior, the next steps become sort of clear. But what we realized was that trying to define crosstalk in a way that did not rely on stability and Markovianity as a crutch was extraordinarily difficult. But if you start by defining Markovian crosstalk, then you can generalize that with only a reasonable amount of difficulty.
Right. So basically you're saying that crosstalk is the stuff that's still there, even if you make these simplifying assumptions. And then you can add in these other processes on top, as would be the case in most real processors in some form or other anyway.
So for real processors, what we do is we look at it, we try to treat it as Markovian. If it's well approximated by a Markovian model, then that's good enough to go with. We can talk about whether there is or is not crosstalk in the best Markovian model. If I have a processor that's radically non-Markovian, all bets may or may not be off. The issue really, just to briefly deep dive, the issue is that when you have non-Markovianity, it means that some part of your processor is coupled to an environment that's serving as a memory.
Sure.
Now, if the qubits share a memory, it is difficult to, like, information can be transferred between qubits through the memory indirectly. And it's hard to figure out whether we should call that crosstalk or not. We found it sufficiently challenging to make a taxonomy of crosstalk for Markovian. So there are more challenges here, is the best way to put it.
Okay, all right. Fair enough.
So I am going to assume that I have a processor that can run circuits in a stable way and that its behavior is Markovian. Now I can get around to defining crosstalk, and I'm going to sort of do it in a couple of layers.
Robin,
yep.
I have a question. Before the Markovian property, you have mentioned some other requirement, like the distribution is stabilized.
Yep.
But how do you define that? How do you can detect that? Like, even with very random circuits, will be like, you look, the output of the bits are completely random, but it's still a distribution and converge to that true distribution. Like, it's always happening. How do you single out like meaningful cases versus this?
Sure.
So
random? We have a paper on that, okay. Which I'm very proud of, because actually we are notoriously terrible at failing to write papers about things. Chris has in fact pointed out that we started writing our first paper together when he had 0 children, and when we finally published it, he had 3. So we actually have a paper about detecting drift, and so there are all sorts of things that could go wrong, but I want to specifically talk about instability over time, about drift over time. Essentially, what we did was we made rigorous the following pretty obvious observation. If you flip a coin 1,000 times and you get half heads and half tails, then it is sensible to say that that is a fair coin, and it sounds like an independent coin, a Markovian coin, right? And you know, those were IID trials. However, if you look at those flips and you timestamp them, and what you see is that the first 500 were all heads, and the second 500 were all tails, it is reasonable to become suspicious about whether that really was an independent coin. You can formalize that using statistical model selection. And so that little nugget is the base of a protocol that we developed and demonstrated in a paper that's also on the archive from last year, showing how to, under reasonable assumptions, detect that a processor is not running circuits repeatably, that in fact its behavior is drifting or fluctuating. That's probably all I have time to talk about right now, but I hope that at least gave you an idea what I meant.
Yeah. Okay, good. Thank you.
Okay, so I have a processor that's repeatable, it's stable, it's Markovian, and now I can finally get around to what it means to be crosstalk-free, which is each layer should be divisible into gates. Let me switch back, I'm going to go back a slide. Here I just have layers, right? Sequence, you know, gate, 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 or layer, 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 layer. These are just sequences of operations. But I want to be able to refine this more, and I want to be able to say that each of these layers is divisible into gates, and that those gates are independent and local, and I'm about to make those terms very precise. This is the essence of a crosstalk-free error model. Anything that violates the crosstalk-free model is crosstalk. So again, to repeat what I just said, each layer should divide into independent local gates. Let me define those two words, local and independent. So we have two conditions about the behavior of the processor that we can test experimentally. The first is locality of operations, and this is cribbed straight from the paper. The physical implementation of a quantum circuit should not, on this processor, should not create correlation between any qubits or between any disjoint sets of qubits unless it's trying to do so, unless it's supposed to do so. So if the circuit contains multi-qubit operations that intentionally couple qubits number 1 and number 4, it can create entanglement or classical correlation. But if you specialize to the circuits that do not have any multi-qubit operations that intentionally correlate those qubits, all such circuits should fail to create any correlation between those qubits. That's a testable condition. It takes a very long time to test it exhaustively, but it's a testable condition. We shouldn't be creating correlations between subsets of the qubits that aren't supposed to get correlated. So that's what we mean by locality.
And by this, you mean classical or quantum correlations, right? Because I mean, in principle, crosstalk can be quite a classical thing and can affect multiple qubits, say, but that would still potentially violate this rule.
So yes, basically, but I'll push back slightly and say, how would I know if there were quantum correlations? The only correlations I can see are correlations between the outputs of the measurements, right? Between the classical bits. And so that's what I can actually see. Now I could start doing, you know, the kind of reasoning that Bell inequality people do to figure out whether at some point there must have been quantum correlations, but then I have to get into like space-like separation. And so really when I mean correlations, I mean things that manifest as correlations between the output bits.
Sure.
Whether they came from quantum or classical, I couldn't care less. This condition says no correlations of any kind. That's local operations. The other condition is maybe not as immediately obvious that you need it, but it's independence. So when an operation, a gate, a state prep, a measurement, when any box that can go in a quantum circuit appears in a quantum circuit, and it's acting on some target qubit Q, like this gate here is acting on qubit number 1 at time t, time 1, the dynamical evolution of Q at t doesn't depend on what other operations appear in the circuit at the same time t. This is basically saying that these gates must be independent of context, that this X gate and this X gate must have the same effect on their target. If this X gate behaves differently from this one, even if no correlations are created between the qubits, that is another kind of crosstalk. That's another violation of the crosstalk-free model. So this really is independence of parallel context. These are the two conditions. This is all that we define as necessary for crosstalk-free. A processor is crosstalk-free if and only if its observed dynamics, when running any and all circuits, always is observed to satisfy both of these conditions. Let me stop for a moment and ask for questions. Great. In that case, I'll sort of roll downhill to the end of my talk. These conditions we show in the paper, they're abstract, they are operational, but they're equivalent to a very explicit, concrete model in the statistical sense that we describe in the paper. And that model, concisely stated, is that every layer has to be described by a CP map that is a tensor product of local CP maps that are independent of context. In other words, there is a CP map describing this X gate that is the same CP map that describes this X gate. And that's, if I didn't have the tensor product condition, then I wouldn't have a CP map describing this X gate necessarily. But I've started by saying it's a tensor product, and then I can say that the components of the tensor product are independent of context, which is not terribly surprising. It's probably what you would have come up with, but we sort of went and built it up from scratch. Crosstalk errors, then, are quantum circuit phenomena. Crosstalk is a physics phenomena. It's different in every physical system. It manifests differently in ion traps, in silicon, in semiconductors, but crosstalk errors are something that QCVV people can get their teeth into. They're described by CP maps. Every circuit layer can be described by a CPTP map if the processor is Markovian. And then, if you know what those are, you can check whether each layer map is local and whether those components are independent of context. If they are, it's crosstalk free. If they're not, you can talk about measuring the distance to the closest model that is crosstalk free, and that quantifies how much crosstalk you have. We also introduced a useful terminology. If you have a violation of locality, for instance, there's coupling that happens between idle qubits. These two just undergo a ZZ Hamiltonian. That's an absolute crosstalk error. But violations of independence don't happen in a single layer. They are, a violation of independence would be if this X gate acted differently from this one without ever causing correlation between qubits. That's a relative crosstalk error because it is relative between these layers. You have to look at two different layers to see it. We also introduced in this paper a lightweight protocol to detect crosstalk errors, and it's implicit in what I've been saying so far. So in order to sort of wind up and give Erik all the time that he deserves, I'm just going to sort of put up this picture and say it involves running random circuits that intentionally never couple regions and then looking for correlations. Now, we might not happen to run the very particular circuit that does couple them, but you can do statistical arguments to say if you run enough random circuits, then you will almost certainly detect this, yada, yada, yada. This is quite a few pages in the paper. We use a graph analysis algorithm to look for correlations, and the results end up looking like this. We've got a graph, a bipartite graph that has the settings on each qubit. So this was for a 2-qubit example. We had qubit 0 and qubit 1. The settings are just what did you run on that qubit. The results are what happened when you measured. Red edges here are correlations that shouldn't exist and were detected by this causal graph analysis algorithm. It worked in simulations. We kept doing it until it worked. We also did it on 6 qubits. It runs efficiently on more than that. So it worked. That's cool. There are a heck of a lot of different kinds of crosstalk errors. But once you've got this paradigm, this framework that I talked about here, then you can actually start listing what they are. And they're all either violations of locality or violations of independence. And that's it. Thank you very much.
I have a question about your independence thing, just before we move on to the second half. So when you originally explained your independence thing, what I took away from it was that you had to assume independence was an assumption or a statement that if I apply X, the X gate on qubit 1, the operation of that X gate does not depend on what I do in that same layer on either qubits 2, 3, and 4 in this picture. So X gate on qubit 1 will always do the same thing to qubit 1 independently of what is done to these other gates. And at some point you started to talk about the fact that in fact independence was whether the X gate was always the same irrespective of when you're doing it. And it seems to me like this is a bit of an easy way to muddy the water in terms of, like, I know that you're talking about a drift-free processor here, but I could imagine a scenario where I'm doing an X gate and whenever I do an X gate on that qubit, it doesn't affect anything. It neither affects anything that is happening on the other qubits, nor depends on what is happening in the other qubits. But nevertheless, if my processor is subject to drift, my X gate at time t may not be the same as my X gate at time t prime sometime much later in the calculation, or indeed in another shot of the algorithm. And to me, those two things are quite very different. They're not only very different outcomes, but they would also require very different solutions. And so it seems like it would be really useful to have those two things being quite separate in the definitions.
So if I go back a bit more, you'll recall, going back, that I made two assumptions. So what we were just looking at, independence, is a condition, right? It's not an assumption, it's a testable condition. I want to know whether or not this is true. And I can do experiments to see whether or not this is true. But I made some assumptions. And one assumption was that a processor should have repeatable stable behavior.
Sure.
Right? So I have assumed away drift. If you tell me that I have drift, let me go forward again. Then absolutely, if I have drift or if I have non-Markovianity, then this gate, this X gate, could be different from this X gate. Notice that they have exactly the same parallel context, but they happen at different times.
Right.
Crosstalk can't cause this X gate to be different from this one, but drift or non-Markovianity could.
Okay,
That's why I assumed that I didn't have any of those. If I do have some of those, all hell breaks loose and the problem gets harder.
Yeah, so this is why, you were, when you talked about the two X gates being different, you explicitly talked about the first X gate and the third, which happen in different contexts. Is that right?
That's right. I have already assumed that the first and the second have to be identical because, going back one step, these are identical layers, right? Yep. So even if the X gate doesn't exist, even if I can't break this up as a tensor product, this layer and this layer have to act identically by the assumption of Markovianity.
Sure. Okay. We're on the same page then.
Brilliant. Any other questions before we switch speakers?
Yeah, I think so. I have a question, but just point out to the rest of the participants that you should ask a question if you have something specific about Robin's talk, so that you don't forget. And since he's continuing to drink his beer, the answer might be coherent now rather than later. So yeah, my question is, I guess a little bit more meta. So is there such thing as logical crosstalk, or since if we created a single logical bit, we've already sort of solved the crosstalk problem at the physical level, and that won't manifest at the logical level.
There can absolutely be logical crosstalk, and I expect that there will be. Some errors tend to get suppressed as you go to logical qubits and as you increase the distance. Coherent errors, for instance, we're starting to become more and more sure that functional error correction that works is going to suppress coherent errors. So for good logical qubits, the coherence of the error will go down faster than the total amount of error. Errors will get stochastic, we think. Other phenomena will probably get worse, or at least very much can get worse as you move up the hierarchy into logical qubits and then higher distance logical qubits. Crosstalk and non-Markovianity are both errors that tend to get induced by hidden correlations in the classical processing circuitry, which means that they can absolutely get worse at the logical level.
Thanks. We'll give a second introduction. So Erik Nielsen, also from Sandia National Labs, will now present on something about onions. Yes.
Yeah. Well, thank you. Yeah, so again, the same goes with Robin. I don't have any beer here, but you're welcome to ask questions during the talk. And oh, and Chris, am I trying to tighten this up and get us out close to on the hour, or is it okay to run?
Yeah, go ahead. I mean, people will quietly leave if they have somewhere else to go. But the video, we'll post a video on YouTube, so that'll be available to at least 7 billion more people than
awesome
21%.
Oh wow, this thing is like going ahead of me. Okay, all right. Well, let me start. So yeah, so this talk is about characterizing qubits using fewer circuits than you might think you would need, and it will have a number of pictures of onions in it. And so I hope you like onions. This is from the same group, the group with Robin, Tim Proctor, Kenny Rudiger, and Kevin Young, this quantum performance lab out of Sandia. So the context here is, well, eventually we'd like to have quantum computers that can solve problems that no other classical computer can solve, right? That's kind of the holy grail. Now, though, I would argue that what we care about is learning about the quantum computers that we have. We have these noisy intermediate scale quantum computing devices, and those devices it's going to be very difficult to find problems that can outdo a classical computer. And so I would argue the thing that we can do with these NISQ devices is learn about what types of noise do they have. How can we make them bigger and better? So that'll be kind of the backdrop of this talk. If you buy into that and say, yes, we do want to run analysis on these quantum processors rather than some, possibly useful algorithm, there are two broad types of analyses you could run. One is benchmarking, where that's focused on finding usually a few different benchmark numbers, and I've listed a few examples there. These are useful things to do. They give us numbers to compare different devices and to know kind of roughly an overall performance metric of a quantum processor. And another nice thing is that they typically don't require that many circuits, and the number of circuits that you would need to run on a computer to evaluate a benchmark is fairly constant and should be about constant with the number of qubits, because you're always evaluating the same number of things, the same number of benchmarks. So that's nice. This talk will focus on the second branch here, the model-based characterization. And that seeks to answer, what is a predictive model that can tell me what the device behavior is going to be? So it is a little bit more ambitious and also requires more resources typically. Gate set tomography is one of these, and this sort of framework that I will talk about in this talk is also in this category. Here, the number of circuits that you need is proportional to the number of parameters in the model, and typically that is something that grows with the number of qubits that you have, because you at least want to learn, one thing about each qubit or something, along those lines. So I mentioned at the bottom, that it's not necessarily more expensive, but typically is. Okay, so what is model-based characterization? There are two steps. When I say model-based characterization, I'm thinking of you take two steps. First, you have a model and you're going to compare it to data and get as good of a fit to the data as you can, given some adjustable parameters in the model. So the model produces these circuit outcome probabilities. It tells you what the circuit outcome should be, and you can just match that with the frequencies that you find in the data. You can optimize the parameter vector of this model, and you get a best fit model that comes out in the end. The second thing that you want to do when we're doing model-based characterization is, and this acknowledges the fact that almost all the time, even the best fit model will be statistically invalid. It won't fit the data well enough that you will say, oh, everything is explained in statistical rigor in the data. All of the data is explained. So instead of just giving up and saying, oh, well, the model's invalid, because then we'd be giving up all the time, we compute the amount of unmodeled error. So here I've put this red W. This is going to be whatever else is wrong with this device that you have, and it's a quantity on a per gate basis. So it's meant to be kind of like a gate fidelity in that it's per gate, but it's additional stuff that your model didn't capture. And so when we compare a model and data here, I'm going to have kind of this thermometer where we've got a certain amount of the error is captured by the model and another amount is not. And that's just going to be some rough number that we have again on a per gate basis. So, okay, so that's model-based characterization. Now I want to go on and talk about how models can be nested. So here's an example. We have a depolarizing noise model at the center of this onion. So here onions are starting to make their showing. That's a pretty simple model. A slightly bigger model would be to allow the different gates to have different depolarizing noise rates. Okay, so the middle model was every gate has the same depolarization rate. Then we could go to gate independent depolarizing noise. We could keep working our way up, building kind of bigger and bigger models, meaning they have more and more parameters, until we get to a model where all of the gates are CPTP maps. And that's what kind of standard traditional GST assumes and uses as its model. You could go even beyond that. Oh, did someone have a question?
This is actually Robin. Did you mean gate dependent on the orange?
Yeah, we've kind of tossed that back and forth. So maybe I do. It depends like how you're, if this means that the gates are independent of one another, and what the rate is depends on the gate. Does that make sense?
I think I just wanted to make sure that that everybody got, and I think they do now.
Yeah, no, thank you. I feel like we've flopped back and forth on that, and I agree. There's probably a better term, and I probably picked the wrong one. So anyway, yes, so that's what it means. It's bigger than the depolarizing noise model, the one that I have in mind. And the last layer I was getting to was you could picture even bigger models than what GST uses, where you can throw in some time dependence and non-Markovianity that you're trying to model. Okay, so a nice thing about this, though, is that these models can be nested, so we can kind of think about making the model bigger or smaller in a nice way. The rest of this talk, which was also a March meeting talk, is going to just be looking at a case study and showing you how we can use this model-based characterization to look at a 2-qubit processor. I have taken 2 qubits and have simulated some noise on them. So I've put in a mix of stochastic and coherent noise, and What those errors are exactly doesn't really matter, but we have some simulated data, and I want you to picture you're handed this 2-qubit processor, and you're asked, well, figure out like what's going on with this 2-qubit processor. What's the noise like in this thing? How well does it perform? What do you do with a 2-qubit processor? So we'll start, well, and you might start by running just standard Clifford randomized benchmarking. That's a typical thing people do. In this case, that's the data that I've taken. I have taken 120 circuits worth of data. Here I have 4 different depths of Cliffords, and at each depth I've taken 30 circuits to give me the 120, and I have 10,000 repetitions of each circuit I performed. And I have this data now. And I fit a decay curve to it to get an RB number of around 0.03. And so already that tells me something about the processor, and that looks, that's definitely giving me some information. What if I wanted to do more and look at this a little bit deeper? So I'm going to take each one of these points in a line here. They're all stacked up because they all occurred at the same depth. Let me expand those out. And this is just artificially kind of moving them apart so you can see them better. And then I'm going to add a 2 sigma error bar on each one. So the error bars are in the success probability. This is about what you would think, how much play you think you could have in that point, and you'd still be sufficiently explaining the data. This is what statistics would tell us, given that we have 10,000 samples per point. And you might notice that, well, the error bars are kind of small there. We've taken a lot of data. Maybe that line doesn't explain everything about this data. And you'd be right. If I take now a depolarizing noise model, so this is one where, if you look to the right here, this is all of the 5 gates I have in my processor. There's X and Y gates on each qubit and a C0 gate. All of them have the same error rate, the same depolarizing noise error rate. I've taken this error model and I've fit the best model that I could to the data. I've picked P error as the optimal P error. And now I have plotted, the blue points are the predictions for each of the success probabilities that I have data for. And you can see that, well, there are some of them kind of land on the points and some of them don't. I want to plot this a little better because it's hard for me to look at these points like this. So let me just put the predicted probability versus the observed probability. So all the points should lie on the diagonal, and there should be a little bit of play in them because there's finite sample error. But that 2 sigma error bar that we're looking at, that's the thickness of this line, which you can barely see. This plot is also kind of hard to read. So what I want to do is I want to just plot the difference in the observed probability and the predicted on the y-axis instead of just the observed. So my next plot does that and flips this down. So now, even though I've not updated the legend here, the title, this is the difference between the observed and predicted versus the predicted. And now I can see this annulus here, the shaded annulus, is where I would expect all the points to lie if they all were within the error bars. So this is just a way of, an easier way of visualizing, do the points that I get from the model, do the predicted probabilities lie within the error bars of the data? And you can see here pretty clearly that they don't. If I look at this thermometer plot down here that I talked about before, there's the error that we get from the model predicts that the depolarization rate is around 0.03, which is like that RB number that we saw. And then the unmodeled error is about 3 times 10 to the minus 3. So that's smaller than what the model, the contribution of the model is, and that's good. So you could at this point just say, well, this is good enough. There's not that much that's unmodeled, and we could call it good. We could also, though, just decide that this isn't good enough and want to improve the model. And that's the path that I'll take in this little choose your own adventure down at the bottom. So let's expand the model one layer of the onion outward to this independent or dependent gate depolarizing model. In this model, you have now, there's a different depolarizing error rate for each of the gates, which is I've tried to pictorially indicate up here. This, instead of just one parameter, this model has 5 parameters, so it's going up. If I look at the points and how well they overlap the error bars, that looks kind of the same. Maybe it gets a little bit better. You can see that numerically, if I look at the unmodeled error in this case, it's dropped from around 3 to 2.5 times 10 to the minus 3. And so it's fitting the data a little bit better. This model explains a little bit more, but not too much. So what do we do now? We could call this good, but let's improve it some more. Let's look at a bigger model. The next model I want to look at allows the stochastic errors to be different for different poly types. So there could be a different rate of X-type errors as there would be different from the Y-type errors, for instance, on the X gate. So each of the gates now has a set of parameters, and there are 27 parameters total in this model. The set of parameters ranges over all of the polys, the single qubits or the 2-qubit polys. Okay, so this one now, if I look at the points, there's not a lot of points that I see that lie outside an error bar. And if I look at it the easier way, you can see, yeah, this model is doing a much better job at describing the data. It does well. You can see that also in the unmodeled error, this W is only 3.5 times 10 to the minus 4 now. So that's good. And so at this point, we could call it good enough, and that's tempting. We could improve the model, but this model already is doing pretty well. Or we could do a harder test. So I want to highlight that up to this point, we have not taken any more data than was required for doing the initial RB. So all of this analysis has been done just with the RB data. We could do a harder test by taking more data. Let's see how this model performs when we take a set of 400 Rabi-like sequences. So these are more periodic circuits that would test, would be more sensitive perhaps to coherent errors. They're definitely a different class of circuits than the random errors that randomized benchmarking has. Okay, so let me breeze through. If I look at now this Rabi data, let me look through the different models we've already seen before. Let's start with the depolarizing noise model, the center of the onion. This is what it looked like on the left is what it looked like for the RB data. On the right is what it looks like for the Rabi data. This plot is a lot bigger because I've maintained the same scale. So the reason this plot is taller is because the points are much further away from the middle. So here we see that this model is the model is even more strongly violated in the case where we compare it with the Rabi data. And again, if you look at the W, this unmodeled error, it's around 0.03, which is about now the same order of magnitude as the depolarization rate is that the model is capturing. If I do the same thing with the gate-independent depolarizing noise, it looks very similar. I won't spend a lot of time on this. It kind of drops this W down a little bit, but it looks very similar. Now let's see what happens with the polystochastic noise. So this did very well. This model did very well for the RB data, but when we look at the Rabi data, it's clearly not capturing all that's in the Rabi data. And again, and you can see that through the unmodeled error amounts here that are around 0.02, which is again around that same order of magnitude as what the errors the model is capturing. So here, now we're faced with this, well, our model worked for RB, but it doesn't for Rabi. What do we do now? We could just call it good enough and say, well, I don't really care about the Rabi sequences anyway. Or we could do what we did before and we improve the model. So we make the model bigger. Let me add to this model coherent errors. So now this model has each of the gates has parameters, all the stochastic noise parameters that we had before in the green model. And now I've added over rotation angles, over under rotation angles for any of the poly axes. Here they are. And so this gives me 54 gate parameters in total. But what it buys me is now, when I compare the best fit model for the Rabi data, I find that it fits the Rabi data very well. And in fact, if it's so well that actually the unmodeled error here goes all the way down to 0. And if I let you in on a secret, that's because the model that I used to generate the data in the first place only had coherent and polystochastic errors. So this makes sense. But in general, you'd probably have some amount of errors still left. So this is good. We could go back though and say, well, so this model now, this predicts and explains all of the Rabi data, but we trained it on the Rabi data. What if we went back and looked at the random data, the randomized benchmarking data? Would this same model, if I fix all the parameters, would it explain that? And the answer to that is yes, it still does. So it's a good check to do. When we look at the randomized sequences, we find that this residual unmodeled error is around 6 times 10 to the minus 6. Okay, so now we have a model that explains both the random and the Rabi-like data. We could call it good, or we could do a harder test. And at this point, in the interest of time, I'm just going to stop and call it good. But I do want to take a step back and look at what is it that we did here. This is the flow of this sort of model-based characterization that I'm advocating for here. We made an initial test. We did 120 RB circuits on our device. We asked, does a depolarizing noise model with one parameter, does it describe the data? No, it didn't describe the data well enough. How about a gate-independent depolarizing noise model, 5 parameters? Does it describe the data? No, still didn't describe it well enough. What about a polystochastic noise model? That one did. So instead of adding another layer at this point, we said, well, let's try another test. So we jog up here and say, let's run 400 Rabi circuits. And we looked at how our current models describe that data without refitting them. And they didn't describe the data so well. So we expanded the model again and tried to fit a polystochastic noise model that had coherent errors as well. And that worked well. And it worked well with the initial 120 RB sequences as well. And then we stopped. So this is the kind of flow. This required just 120 RB circuits, which is something very common to do. And then 400 Rabi circuits. So the conclusions here, one of them is that you may not need as many circuits as you think to get good characterization information out of a device. In particular, using these models can really give insight. Even using just the RB data, for instance, we can gain a lot more insight into the processor than just doing an RB benchmark analysis on it and getting a single number. And it was interesting to show that the unmodeled error can be quantified. That's a key piece to this. And something that, I haven't gotten into much, but is a talk in and of itself. And it gives, the model-based approach gives us a lot of freedom. I chose very standard type models, but you could choose physics-inspired models where you know what the type of noise is in your gates, and you can add that into your model. So there's a lot of flexibility in this approach. There's a couple things that I just want to highlight in closing. The depolarizing noise model that we got from RB, that would be the standard model that you would take. You have an RB number. What does that mean? The device is like? Well, it means that there's on average, that's the depolarization per gate. If you do that and you get a depolarizing noise model, that doesn't necessarily predict all of the RB data to statistical precision. That's just an interesting point, because I think that it can be kind of assumed that, well, at least the RB data is well explained by the kind of RB inspired model of depolarization noise. That's not true. The second is that scatter in the RB data doesn't imply coherent noise. So if you remember the green model that we looked at, that entirely described the randomized benchmarking data, and it was just stochastic. The model had just stochastic errors in it. The errors on the device had coherent errors, as the Rabi sequences unveiled, but scatter in the RB data did not imply that there was coherent noise. And last, just that the RB data is often sufficient to construct one of these stochastic noise models. And that's just another way of saying we were able to go quite a long ways just using the RB data and analyzing it a little more fully than just doing a fit to the RB data with the exponential. So I think that's the talk. I would love to take any questions. Where we're at here.
Yes, thank you for the talk, Eric. Are there any questions from the audience? Because I have one I'm dying to ask. So I'll ask it now, unless someone unmutes themselves. So I'm wondering how, when we look at these, especially detailed models, physics-based models, like how detailed access or control over the physical device do you need to perform these experiments? And are we moving to a place where people who are trying to think about this kinds of research are being more and more removed from these devices, so that maybe they're closed off for commercial reasons or whatever? Like, do we need to start thinking about how we're going to evaluate the performance of these things, or even help in the development of them when we have maybe a more closed access or relationship with the devices?
Yeah, no, one of the things that we have run up against when we run circuits on actual devices is the way that the compilers can want to optimize things. So maybe we want to see how the idle gate performs. And so we try to do 10 idle gates in a row, and the platform, right, will just sort of compile those away and won't do anything.
Right.
And so, yeah, that is I think that there's some recognition that is something that should be open to researchers, but I think you're right that it is harder to access that than you might hope. And often, I think so far, I would say that we have been able to still run the circuits that we'd want to on these devices, but that it requires some kind of tricks in telling the compiler essentially not to do anything. So yeah, I think it's a good thing to think about going forward. A lot of this work, when we're comparing to models, the model has some gate level picture of what the device is doing. And if it isn't really doing those gates, it makes it hard to pick a good model. Like this framework would still work and that the models would still fail. You would know that if things went wrong, but it would be just harder to, it's very hard to write a model that somehow accounts not just for noise in the gates, but also like actions taken by a compiler. So that's throws a wrench in things.
Okay. All right. Well, thank you both to Eric and Robin for the wonderful Sandia National Labs doubleheader. And we'll see everyone next time. Thanks a lot, guys.
Thanks for the invitation, Chris, and thanks to everybody for listening. And if you have any further questions, send us an email.
Yeah, please do.
Or comment on the YouTube video.
That's right.